So, hello everyone. I am Fabien Mathieu, and my current affiliation is the links, and just the links. And today I'd like to present you work I did jointly with Céline Comte from the University of Eindhoven and Anna Buzic from INRIA and NS. And this work will be about stochastic matching. So I will first go to explain about what is exactly a stochastic matching, and we'll introduce our motivations, our model, blah, 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 blah. And after that, we'll go into the hardcore stuff. So I plan for this presentation to do to limit the technical part to the smallest amount possible. I hope it will be accessible for everyone. But we will gradually increase the technicality as the talk goes on. Okay, so the introduction, stochastic matching. So what's this? Well, I always like to go back to the original, the seminal paper from Gale and Shapley from '62. And it was about something called stable marriage. So yes, of course, it was kind of sexist. It was a model with man and woman, and you wanted to match them together. So you had some constraint, which was called a compatibility graph, which explained which man was acceptable for which woman and vice versa. And you also had some preferences because some partners were more attractive than others, and depending on, of course, the eye of the person who made the evaluation. And the output of the Gale-Shapley problem was to find a matching, that is a set of marriages, in which you were able to avoid any kind of affair between two couples, where one member of the couple would prefer another member from another couple instead of a current partner. So this is the basic problem. And since half a century, it evolved with many variants. For instance, one of them is the B matching, where you are able to have, say, multiple partners. And actually, it had a lot of very useful applications in real life. So for instance, in the US, it's something called the hospital residence problem, where when you have MD students that want to apply to some hospitals, how to make the allocation in order that everyone, both residents at hospitals, are happy in the end. In France, you've got, I don't know if you can call that successful, but a famous application which was previously called APB, Admission Post-Bac, and it is now called Parcoursup. And in fact, the algorithms should be the one from the B-matching theory. There was a lot of work on the case where the compatibility graph is not bipartite between men and women, or hospitals and residents, or clients and server, but was non-bipartite. There was a field of application which was peer-to-peer networks, because in peer-to-peer networks, both peer-to-peer softwares are simultaneously clients and servers, so they can match pretty much any way they want. And another example, and we'll go on that later, is the kidney exchange program. And there is also the dynamic matching, which is the case where instead of having just one static set of people you want to match, this set evolves with time. Some people, when you match people, you remove them from the system, new people arrive, and the set of application is basically the same as for the previous evolution, which is, say, peer-to-peer networks and kidney exchange programs. Okay, so about the kidney exchange program, just the very basic example is, imagine you've got Alice, she needs kidney, and she's blood type A. She's got a friend, Bridget, that is willing to give a kidney, but sadly, Bridget has blood type B. So she cannot give a kidney to Alice. On the other hand, you've got Bob. Bob needs a kidney and is blood type B. And he's got a friend, Alfred, a brother, sorry, the brother Alfred is willing to give a kidney, but his blood type is A. And this is what the kidney exchange program is about. Maybe you should be able to match Alice and Bridget with Bob and Alfred in the way that each one gets the kidney from the other's donor. And so this is a matching between pairs of people. And it exists. It is already applied since more than 20 years, I believe, something like that. There's a lot of literature about that because, yeah, it kind of saves lives. And yes, there is some URL if you want to go deeper on that. Sadly, the thing about kidney is that it's kind of a heavy subject. I mean, it's life and death matter. So for this talk, I wanted to have a more lighter example with ice creams. So you imagine that you've got a vendor of ice cream, and what she sells is 2 scoops ice creams, you know, with 1 scoop and 2 scoops. And she has boxes. So 4 boxes of chocolate, 4 boxes of vanilla, 3 boxes of strawberry, and 1 box only of lemon. And she doesn't want to sell every combination because she thinks some taste bad. So she only offered 4 combinations: chocolate vanilla, vanilla strawberry, chocolate strawberry, or the famous strawberry lemon. And she's got 1 employee that prepares the scoops, and they will prepare the scoop 1 by 1, just by picking up a box, making a scoop, pick up a box, making a scoop, and so on and so on. And another employee has for only job to take scoops, 2 scoops that fit for the compatibility, and make a 2 scoop item. Okay. And then what happens? The vendor, she thinks, okay, I've got 1 box of lemon only. I fear that I may fall out of lemon. So I will ask the guy who assembled the scoops to avoid using lemon if it's possible. Yeah. So if I do that, it will ensure me that I will limit the chances to have no lemon at end before the other stocks are exhausted. Why not? So yeah. And this will kind of be our running example for the talk. Okay, so I know that some of you want some real mathematical models, so I will go through the necessary steps. So the compatibility graph, so which pairs of scoops are allowed in the cab. It's a simple graph. That is, you don't have any loop. You cannot make chocolate scoops. And I just describe the scopes that you are allowed to do. So traditionally, it's G equal VE, and the number of flavors is N, and the number of combinations is M. Then you've got the arrivals of scoops. It's the guy that makes the scoops from the boxes. And so the theory is it's a positive vector of arrival rates of scoops. And we assume that these arrivals are decreased by some independent Poisson process. So far, so good? Yeah. And last but not least, the policy. So the policy is the person that assembles the scoops. And so formally, it's a Markov chain that describes the way you do the matching. And among them, you've got a subcategory of policies, which are called greedy policies. And greedy policies, there is just 1 rule, which is if you can make a pair of scoop, you make a pair of scoop. You don't delay until something's happened. You make it as soon as possible. You cannot leave a situation without making a pair of scoops that you could have done. Okay. So we've got the systems, this stochastic matching model. And what are the type of questions that we want to ask and to answer? Well, the first most obvious question is, will I have to throw away scoops in the end of the day? And yes, for scoops, it can be important. For kidney, you can imagine that it is even more important. And so this raises the question of stability. And stability actually comes in many flavors. So if you consider the compatibility graph, variable weight, and the policy, does it make a stable system? First question. Stabilisability. If you know the graph, can you find out a way, a proportion of arrivals and a policy such that it is stable? And if you know the graph and the boxes of ice creams, can you find a policy that ensures that the result is stable? And still speaking about stability, you've got maximal stability. Can you find a policy such that anytime a graph and arrivals are stabilizable, that can be stabilized by that policy? Okay. So first question about stability. Second question is about what types of two scoops will you produce in the end? So you can look at the departure rate, which is the number of two scoops you make, and questions, natural questions. Can you predict that rate? Can you change it a little bit in one way or another way? And this is the questions you want to ask. So for the ice cream, for instance, vendor, it's kind of if one of two scoops can be sold at a higher price than the others, can you tweak it to produce more of those? Okay. So we were not the first to come into this thing. There was a lot of results. I will probably forgot many of them, but I will just recap the most important one for our work. First result that exists is about the stability. And the result is the graph is stabilizable if and only if it is non-bipartite on each of its connected component. And the intuition is that when you're bipartite, all fields go to hell, because basically it means that you got demands on one side and offers on the other side. And if you have an lack of balance between demands and offers, one side will grow arbitrarily large. And even if you've got a perfect equality, because your arrival rates are kind of Poisson, you've got sort of, not a sort, you've got a random walk that occurs between demands and offers, and it can grow arbitrarily larger. So if you've got something that is bipartite, basically, it will be impossible to stabilize it with Poisson arrival. You can have solutions where you kind of couple the demand and offers arrival, but if you don't do that, you cannot ensure stability. Okay, yeah.
Just one question. So essentially, when you have a bipartite graph, let's say O is equal to 1.
Yeah.
So the core of the problem is this random walk
exactly.
for the difference between demand and offer. And if you just normalize by that in some sense, I say, okay, I accept that at the end of each day, I will throw away the difference between the demand and the offer. Do you have a notion of stability?
Yes. So usually, Anat, you don't hesitate to correct me, but what you do is just you make arrival of pairs of one demand and one offer. So this is the usual trick to be able to study stability. But yes, and otherwise, for any type of queuing systems, the simplest way to ensure stability is to enforce of kind of abandonment. So abandonment, you know, like, okay, I give up, or you, like you said, you throw away the scoops into the trash because, yes, that kind of stall. Yeah. Good.
Yeah, but does it ensure that, for example, if you have an excess of demand on the long run, for example, you will be able to throw away only on the demand side and never on the offer side, which would mean that you have a sort of stability.
I saw, honestly, it's a 50-50 that I answered wrong. So there must exist an answer to your question.
Okay, thank you very much. I'm delighted to know it.
Yeah. And so you've got a non-bipartite graph, and you can ask a question. You've got verifiable. Okay, does it work? Can you find a policy that works? And for that, you've got a nice formula, which is for every independent set of a graph. So an independent set is just a set where each member is not a neighbor of another member of the independent set. Basically, you don't have two neighbors together. Okay. So for every independent set of a graph, the sum of arrival inside this independent set is smaller than the sum of arrivals in the neighborhood of the independent set. So this is a complex definition, but the intuition is actually very simple. Anytime you want to say we need to have a row smaller than 1, that is less demand than offers, it is the case. So for instance, if I take this graph, you want the arrival of strawberries to be less of the sum of vanilla, chocolate, and lemon. You want the arrival of lemons to be less than the arrival of strawberries, etc., etc., etc. So each time you want to say we need to have row smaller than 1, you have to have row smaller than 1, and it kind of obvious that it is necessary. And the nice thing is that it is also sufficient, actually. Okay. Oh, does it make sense to for those who remember? And so you've got this condition, and what can you do with this? Well, you can just with brute force check it. The advantage is that you really feel what's happening, and you will be able to know the areas of the graph where things where L breaks loose. But it's expensive because of the number of independent set of a graph. It's complex to compute. It's to be something I don't know. It's not free. There is a simple solution, which is you take your graph. So basically, you do some mojo on it. You convert it to a bipartite graph, and you do some kind of conversion, equivalent conversions. And in the end, you get a polynomial algorithm that tells you if this is verified or not. The problem is that you do so many conversions that the intuition of why it is wrong, it's lost in the way. And a last condition, so I believe it was Céline that finds that, and we will come to that later, is, okay, can we have a positive, that is strictly more than 0, flow on the system? And yes, that's it. So that's 3 conditions, and equivalent conditions that we can use to verify stabilisability. Side note, if you've got a stabilizable graph, there's always very simple arrival rates such that J mu is stabilizable, which is you take rates proportional to the degree of a node. If you do that, in the end, you will have a positive flow, which will be 1 on each edge. And so it will ensure stabilisability. Okay. Last result is about maximal stability. I think I will never be able to do that correctly. So yeah, maximal stable. So then again, it's a non-result, but it's kind of very useful for simple graph. And big emphasis of simple graph. If you don't do that, this does not apply. You've got 2 policies that are known to be maximally stable. First policy is just match the highest heap of scopes, which is called match the longest. And the second one is match the most melting scoop, which is called first come, first matched. And so if you do that, And if your graph and arrival weights is stabilisable, your system, your model will be stable. Okay, so now we can slowly enter the core of our results, which are centered about the conservation law. So to speak about conservation law, I will introduce the incidence matrix. So it's a kind of second degree cousin of the adjacency matrix. It's a matrix between nodes and edges of a graph. So the shape is number of nodes times number of edges. And when the entries are 1 if a node is and an edge are linked together, are adjacent, and 0 otherwise. And for simple graph, it's very easy to see that each column sums to 2 because each edge connects exactly 2 nodes. And conservation law just amounts to saying that if you've got a stable system, a stable model, then the flow of departures lambda times the incidence matrix must be equal to the arrival weights. So nothing is lost, nothing is created, everything is matched. And the question we wanted to address in this work is, what can we extract from these equations? What kind of information lies there? Yeah.
Say if then, am I supposed to understand that it's not an equivalence?
Between what and what?
Conservation loss, if blah blah blah, then blah blah blah.
Yeah.
Is the converse true or?
Well, we will see that not necessarily.
Okay.
For instance, here, here, I don't ask for the flow to be positive. Could be negative. Yeah, so you've got this type of things. And actually, the core of the work is to describe exactly in which case we can go the other way around.
Fabien, sorry,
yep.
Go back, please. I just have a question about simple graph. Each column sums to 2.
Yep.
What does it mean and not simple graphs?
Well, you've got 2 types of things. So you've got graphs with loops. So if you got a loop, it is a 1 and 3, or it can be a 2 and 3, it depends. And then the more general way of expressing graphs is hypergraphs, where basically the matrix can be filled with arbitrary integers. And for each edge, you associate a subset of nodes, possibly with multiplicity.
Okay.
Yeah. And yes, I forgot, in all this framework, hypergraph or supergraph, we have no notion of direction. It is not a directed graph, and in particular because natural generation is hypergraph, and for hypergraph, speaking of direction is kind of difficult. So yeah. Okay. 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 Now I will speak of the objectivity of the graph. So sorry, we don't have a proper name for that yet. So this incidence matrix, you can think of it as a linear application between the space of edges and the space of nodes. And like all linear applications, it can be injective in the sense that for each vector of nodes, you have at most 1 vector of edge such that the equations is valid, or it can be surjective in the sense that for each vector of nodes, you have at least 1 vector of edges such that the equation has a solution. And of course, it can be mixed, so you can have injective only things, that is things with injective but not surjective, bijective, when you've got both injective and surjective property, surjective only, you're surjective, but you're not injective. And yeah, like I said, we lack names for that. And non-injective means that it's not injective and not surjective. And by metonymy, so we say that a graph is surjective, injective, whatever, if the underlying linear application is surjective, injective, whatever. Okay? So this is the time where we try to see if you're awake. So see this compatibility graph between flavors. What do you think it is? Is it injective, bijective, surjective, non-injective?
Cannot be bijective because there is one vertex less than
edges. Yeah.
I don't remember the sense injective and surjective,
but it's a good idea, yes. So it's not surjective.
I don't remember between the left and the right which is which, but
yeah.
Maybe it's one, but not the other.
No one wants to bet. Okay, so the answer was injective only. It is injective because if you've got a vector of edges such that ay is 0, y must be 0. For instance, if you look at lemon, if the number of lemon is 0, because you can only reach lemon from this edge must be 0. Same there, same there. So each of the edge must be 0 if the result is 0. It is not surjective because if the arrival rates of vanilla is not equal to the sum of arrival rates of strawberry, lemon, and chocolate, it will not be able to match, and you will not be able to construct a solution. And we'll see, back. This is injective only. Yes, the package says so. Okay, this one is called a diamond graph.
Because there is one. Yeah, just the cardinality doesn't match. So.
Okay. So it is surjective. Surjective because if you've got xa that is equals to 0, then x must be 0. One way to do that is to consider, for instance, one triangle. And if you look at what happens of triangle, it's basically a matrix with 0, 1, 1, 1, 0, 1, 1, 1, 0. And it's very easy to inverse that and to be able to reconstruct. So basically, if you solve the system on one triangle, you find that it must be 0, and you've got you can cover the things by triangle, so it is 0. It is not injective because if you take, for instance, +1, -1, +1, -1, and 0, you will get 0 in the end. So you will have a non-zero solution to a y equals to 0. Okay. This one. Here you've got as many.
-1, 1 -1. No, 1 -1, 1 -1. So it's not injective. Because you have this flow where you alternate 1 and -1s.
So it's not injective. Is it surjective?
And,
if it is surjective, it is also injective because I think because there is the same number of edge and node.
Yeah, right. Yeah. So it's not one, so it's not the other either.
Yeah, and actually it's non-injective. So like you said, you can combine multiple solutions by alternating weights on the outer on the cycle. And it is not surjective. So the way to see this is that for some things to be 0, for solutions to exist, the strawberry plus the vanilla must be equal to the chocolate plus the lemon. And if you don't do that, because it's a bipartite graph, exactly. So can non-injective. And so our running example, so it should be easy, no? I told you there were 4 types possible. We saw 3 of them. And basically, yes, so this case is the bijective case because the incidence matrix is actually invertible. So one way to do this is just look at the incidence matrix in the I and say, yeah, you can inverse it, no problem. And you can ask the package and say it's bijective. Okay, so a little bit of, I will try to shrink that for me. Yes. So a recap for a connected graph. Being injective means that you have at most 1 cycle, and if you've got 1 cycle, the length is odd. Injective only, that means that you're a tree. Period. Surjective, it exactly means that you're non-bipartite. Surjective only, you're non-bipartite, and you have at least 2 cycles. Bijective, you have exactly 1 cycle in your graph, and the length of the cycle is odd. And non-injective, that means that you're bipartite, and you have at least 1 cycle, which is necessarily even, actually.
Sorry, question, Fabien.
Yep.
When you say bijective contains exactly 1 cycle and its length is odd, implies m equal n, you assume that the graph is connected?
Yes. So actually, you see it's the title there.
Okay.
Yeah. And if you want to consider multiple components, well, you have to deal component by component. For instance, being surjective on a multiple components graph means that each component is non-bipartite. Being injective only means that each of the connected component is a tree, etc., etc., etc. So you've got to see in which way you do, if you do intersection of union. But basically, for injection, bijection, and surjection, you need the property to apply on each connected component. Okay.
Really? To be, for example, injective only, you could be each component could be bijective, and one of them could be injective only.
Oh yes, you're right. I was exactly saying you must be careful for when you do intersection and when you do union and splash. Yes. So yes, you're perfectly right. So for injective and surjective, you need to apply that on each component. And for the rest, okay, you do your best. You do your logic. Yes. Sorry for the mistake. You're totally right.
Yeah, no problem. I get it.
Yeah. Okay. And now we've got these tools, we want to revisit the concept of stability. So stabilisability, in terms of the conservation law, a graph is stabilizable if and only if it is surjective. And you don't need to consider the individual components. You don't need to make the mistakes I just made. Okay. You want the applications to be surjective, period. And if you've got a surjective graph and a given arrival rate, it is stabilizable if and only if you can find a positive solution to the conservation law. And the intuition is that with the incidence matrix and the conservation law, you've got every bit of information required to consider the properties of a graph. Okay, now I will do a brief introduction with a specific case of bijective graph. So number of nodes is equal to the number of edges. You've got only 1 cycle per connected component, and the length of that cycle is odd. And for that type of thing, you just have to compute the only solution and just check if it's positive or not. And in fact, you don't even need to do that with brute force by inverting in NumPy your matrix. You can just do that by looking the graphs into the A, because a bijective graph, it's basically 1 cycle with some trees attached here and there. And For each tree, if you start from the leaf, you can deduce the flow edge by edge. So you remove the flows until all you have is one odd cycle. And for the odd cycle, you've got this magic formula that tells you how to do it. So basically, for each rate, if it's your neighbor, it's 1/2. It's the neighbor of your neighbor, it's minus 1/2. If it's the neighbor of a neighbor of your neighbor, it's 1/2, etc. You alternate plus and minus depending on the distance between the edge and the nodes of the cycle. You don't forget to remove the edges from the trees before you do that. This is why you've got a bar there. It means you have removed the part that came from the trees. And here you have. So you see it's kind of, yes, direct way to compute the inverse. Okay, so for instance, if I've got 4 of vanilla, 4 of chocolate, 3 of strawberries, and 1 of lemon, what's the stable solution?
1, 1, 3.
Yes. So I will just blah blah blah. Yeah. So it's 1, 1, 1, 3. And actually, so this is necessarily 1 because you just have 1 lemon. Here, actually, you have 2s. So for here, the formula is 4 plus 2 minus 4 divided by 2. For this, it's the same. 4 plus 2 minus 4 divided by 2. And for this, it is 4 plus 4 minus 2 divided by 2. Just simple formula. Okay. One disclaimer about bijective graphs. The fact that you have only one feasible show does not mean that all policies are the same. Some policies may induce larger heaps of scoops than others. And in fact, you may have unstable policies. And so if you remind, at the beginning of the talk, I told of a vendor that wanted to spare the lemon stock. And so she asked the assembler to avoid producing scoops with lemon if possible. And so this is what will we do. So basically this just said, okay, if you can avoid lemon, avoid lemon. It work? Will it work? It does not work. As you can see, the flow between the flow of lemon strawberry scoops, pair of scoops, is not 1, it's less than 1. Actually, it's 9/11. And so you missed some stock of lemon there. And if you just opted to choose the most melting scoop, well, 0.999 actually is just numerical fluctuations due to the Poisson arrivals, but in the long term, it's 1, 1, 1, 3 exactly. And so, sorry. So you try to be smart there, but in the end, you ended with wasting lemon, while all you needed to do is just choose the most melting scoop. Okay. 20 minutes for the hardcore part of the talk. I don't see what will go wrong. So now we'll have a focus on the surjective only graph. And so to do that, we will add one flavor, which is chocolate lemon. Yeah. I don't know, maybe it's good, but for the purpose of the talk, we say that it is good now. And we'll discuss about the flow of a surjective only graph. So because it is surjective only, for each arrival rate, you've got an infinite numbers of solutions. Of course, you'd like to find a positive one. And maybe you'd like to be able to explore the solutions to find one which is optimal in some sense. Okay, so this is the roadmap of this part of the talk. We'll first discuss how to find a solution, positive or not. We'll discuss how to describe the kernel of a linear application, because we're surjective only, so you've got a kernel of solutions. And if you've got the two things, one particular solution and the kernel, you will be able to describe all possible solutions as the sum of one vector of the kernel and one solution of the conservation law. So this will give you a hyperspace, affine hyperspace of solution. And from then we will want to extract the positive part of the hyperspace, the part that is positive or non-negative for each component. It will be a polytope. And then we'll discuss about extracting the vertices of that polytope. And then we'll say, okay, but what can we reach using actual policies inside that polytope? So the flow space, the first part. So the rates for this example are now 5 of chocolates, 4 of vanilla, 2 of strawberries, and still 1 of lemon. Yeah, we kind of tweak things to be able to show things. So to find a solution, the easy way is to use what is called the pseudo-inverse or Moore-Penrose inverse. So basically, it's a classical linear algebra trick to be able to reverse something that is surjective. So this is the formula. It's kind of cheap to compute. It's not hardcore numerical computation. And it leads to the optimal least square solutions of the conservation law. The only drawback is that it is not necessarily positive. For instance, if I compute the pseudo-inverse for this example, I've got 1 negative edge. If you want to do something that will directly give you a positive solution, what you need to do is a bit of linear programming. It's not that difficult. You just want to maximize the value of the minimal edge, subject to the constraint that you want to be a solution of the conservation law. And in fact, it's a textbook linear programming. With SciPy, it takes 5 lines to program, very easy. It's still polynomial, a little bit more complex, but still polynomial. And the nice thing is that if this is positive, you've got a positive solution. And if a positive solution exists, this must be positive. This is the highest positive solution that exists by definition. And for instance, for the same graph, so this is the maximum flow. So as you can see, the minimal weight on edges is 0.5. Okay, so you've got your solution. Now, let's discuss about the kernel. So we saw one kernel earlier, which was a case of having an even cycle. And when you've got an even cycle, by alternating +1 and -1, you can produce something that will sum to 0 on each node. So this is one type of kernel vector. Another type, so it's what we call the kayak pedal. So basically, you can have 2 cycles of that must have odd length, and you can connect them to a path. And then you can see that with proper assignment of +1, -1, +2, -2, you can have something that such that for each node, the sum of incoming edges is 0. Okay. So we've got these 2 nice examples, relatively simple, and we've got one nice result. Kayak paddles and cycles is all what you need. What I mean is that the kernel can always be described with a basis of kayak paddles and even cycle. So you don't need anything more complex. So for instance, this is a codomino graph, so it's a little bit bigger, and one possible basis. So it's one inner cycle here. It corresponds to alpha 1. So you see it's alternative cycle, and one kayak pedal there with just one thing there. And for any simple graph, you will always, if it is surjective only, you will always be able to provide this type of decomposition. So that means that the flow space, you can always describe this like one solution and then the effect of each vector of the kernel basis. So it's a very compact way of visualizing the possible solution of the conservation law. Now we'll discuss about the polytope associated to that. So we've got this set of equations, and if you want them to yield a positive or a non-negative, it comes into the two flavors flow, each edge will induce an inequality. And if you've got a space and some inequality that splits the spaces in half everywhere, what you get in the end is called a convex polytope. You know, like a cube, a house, a pyramid, everything you can think of. And this polytope, so, is actually the set of positive flows. And among this polytope, the points, the flows of interest are the vertices. The vertices are the extreme point of the polytope, the corners of your pyramid, the corners of your cube. And they're important because if you've got all vertices, you actually have the full description of the polytope. You just have to compute the convex hull of the vertices. And usually, if you want to make some optimization on the weight of edges or something like that, the solution can always be a vertex. You can have solutions that are not vertices, but one of vertex will be one of possible solution. So another, a definition that comes in the middle of this talk. The graph of a vertex is the subgraph of the original graph where you have removed the null edges. That is the edges where the vertex gives a value 0. Okay. And if you look at that, we proved that the vertex only comes in two flavors. Actually, the vertex is always injective. The graph of a vertex is always injective. You take the graph, you take a vertex, you remove all the edges where the vertex is 0. What remains is an injective graph. In particular, so it's either bijective or injective only. Just a quick warning, the number of vertices, it's not my fault, it's because of convex optimization. It's something that kind of explodes with a number of dimensions. So the vertex approach, it's something that you can use, say, up to dimension 14, 15, never go beyond 20. And yeah, so it's a kind of limited approach, but still it offers some perks.
Sorry,
yeah.
Just to be, I think I'm okay, but when you say the graph of vertex, blah, 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 it's a vertex of the
polytope. Yes, the node refers to the graph. Okay. A vertex is always a flow. Okay. Yes, vertices are flow. Positive solutions of sorry, non-negative solutions of the conservation law. Okay, so the quiz time. So this is your model. So you have the particular solution and the kernel. Which are the vertices of this polytope? Actually, it's a polytope in dimension 1, so it's a segment. But yes, can you guess the endpoint of a segment?
In the bottom, it's 1 minus alpha 1.
Yeah. So yeah, I know the police is a shit. 1 minus alpha 1, 3 plus alpha 1, 1 minus alpha 1, plus alpha 1, 1.
So it's 0 and 1.
Yeah. So 0 and 1 exactly. And actually, one of them will be bijective, and one of them will be injective only. And I will just show you the two vertices. So this is the first vertex, the bijective one, and you see that the non-null edges form a bijective graph. And this is the second solution. And you see that here, the non-null edges are a line, that is a tree, that is a bipartite graph. Okay. And actually, now you should have maybe a perfect view, but a pretty good view of a positive solution. But we never said anything about the fact that one particular solution could be reached. And so this is the question, which parts of the polytope can we reach with actual policies? And for instance, if there is one solution that you want, can you reach that? One useful property, which we prove in the paper, is that the set of achievable flows is convex. That is, if you can achieve rate lambda1 and if you can achieve rate lambda2, you can achieve any rates in between. Yes, you just have to mix properly the two associated policies, and it's a little bit tricky, but can be done. Okay, so yes, it's okay. First part of this subset part, which is the last subpart. We only have two subpart left. Don't worry, two subset parts. What can we do if we say the policy must be greedy? Because greedy is nice. Some of the most efficient policies on simple graphs are greedy. FCFM, match the longest, it's greedy. And it gives a feeling, okay, we didn't waste any time because, yes, we were able to match as soon as possible. So you've got a feeling of optimality. And it's not the same as a guarantee of optimality, of course. But what about greedy and achievable flows? Well, what we can be proved is that the set of greedy flows is a subset of the positive solution. That is, each component is positive. No zero, nowhere. And for very, very, very specific cases that we had to craft by hand to produce exactly the results we wanted, we can have equality. We have some situations where with greedy policies, you can reach, for instance, the full segment, except the border, except the vertices, of course. But honestly, in most cases, the subset of flows that you can reach with a greedy policy, it's usually much, much smaller than your actual polytope. And the intuition there is that when you're greedy, you have some obligation. You have some obligation to do some matchings, and it kind of remove some of the freedom that you may wanted to use to be able to reach some specific flows. So I'll just give you two examples. First one is the complete graph. So the complete graph, you've got 4 nodes, 6 edges, it's surjective only. So you've got a nice 2-dimensional polytope, which is a triangle actually, but we don't care. And so this is the polytope of the flow space there. And okay, so if I run one greedy policy, FCFM, I've got this. So for instance, for chocolate, 617, 309, 1 year. I will choose another policy, which is random node. I could do priority, but I don't. Blah, 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 blah. It work, should work. To reversals. And 062. And so basically, what you should observe is that you've got the same result. And this is not a mistake, because if you got a complete graph, and if you match everything that you can match, at any time, you can have at the most, what is blah, blah, blah. You cannot have more than one non-empty set of scopes. Because if you have 2 non-empty set of scopes, you can match them together. If it's good, you do that. So when you have a new scope that arrive, if there's nothing to match with, okay, you do nothing. But if you can do a match, you can only do one match, so you have no choice. And thing is, for complete graphs, there is actually only one greedy policy. All greedy policies are exactly equivalent. They just don't give the same rate, but are the same policy, exactly. And so you've got one dot of solution achievable by the greedy policy against 1 triangles of possible solution. Another example is the diamond. So here, like you saw, one of the vertex was this one. So this is a vertex of the diamond. And you want to be able to reach that vertex with a greedy policy. the best thing you can do is say, avoid these two edges whenever you can. If you have a choice and you can avoid this, do this. So this is actually exactly what this is doing. And so we were supposed to zero this edge. And in the end, you see that this is not zero. And this is not a numerical fluke. Actually, you cannot go beyond that value. So this is a limit case. You can do whatever you want. You will never be able to have less than 0.08 on that specific edge. You cannot zero it. And then you've got the generic policies. So non-greedy policy. And for this, actually, things are much better because there are the value, at least the polytope of positive solutions. Any positive solution can be reached by a non-greedy policy. And actually, in some cases, that can cover some of the borders, some of the non-negative values of the polytope. And the key for this, so it's the convectivity of solutions and the study of the vertices. So I told you that you have two types of vertices, bijective vertices and injective only vertices. And if a vertex is bijective, that means that if you remove all the null edges of a vertex, what remains is bijective. So it's stabilisable. So just what you need to do is to forbid the use of the null edges and use any maximally stable algorithm you have, for instance, match the longest. So bijective vertices can be reached by non-greedy policies. And the other case is injective only. So bad news in that situation, you can prove that it is impossible to reach exactly that vertex. The intuition is that if you forbid the edges, what remains is a tree on each compatibility on at least one compatibility bond, and you will have the drift of a random walk that will happen on the tree, and because of that, the policy will not stable. But the good news is that you can approximate this just by saying, okay, we forbid the edges as long as the system Q's are not too big. And if it goes too big, okay, we allow the edges again until it goes down above the threshold. So we put kind of threshold to determine if we forbid the edges or not. And with that, by adjusting the threshold, we can get arbitrarily close to an injective only vertex. Yeah, so this is just for the show. We take the bijective vertex from earlier, and we apply a semi-greedy policy where we forbid the edge that we want to forbid. And you see that you've got the result that you want, and that in terms of stability, you're okay. You've got small q's, that's a good sign. On the other hand, if you make the same thing on the injective only vertex, well, of course, by definition, you will have zero matchings during the forbidden edges, but the price will be that your system will be unstable and the Q will go to infinity slowly, but to infinity nevertheless. But if you put a threshold, for instance, threshold to 50, you will have an approximation of what you want. We'll have a little bit of flow that will go at the forbidden edges, but you will have a complete control of the Q sizes. So in this simple example, it's virtually impossible to go above the threshold. You can have examples where you can go a little bit above the threshold, but basically the threshold is a kind of frontier where you will stop the non-stability of a process. And below the threshold is where you will be able to behave like if you forbid the edges. And that's it. So if you slept during this talk, what you should tell to your friends when you have to tell what it was about was that the stochastic matching problems were revisited by using the conservation law, the fact that the departures and arrivals not equal in a stable solution. For bijective graphs, we showed that there was one feasible flow, and we showed how to construct it. For surjective only graphs, while we describe the non-negative conservation flows, we kind of give the intuition of why greedy algorithms were not very good of exploring the possible positive flows. And we showed you that semi-greedy algorithms are a powerful class of policies that are able to really explore the set of solutions, positive solutions. So there is a technical preprint available on HAL if you want to see the math part. If you want to look at the code that was used for this presentation, so it's on GitHub, it's the stochastic matching package. It allows to compute vertices, to make simulations of policies, well, pretty much everything you saw during this presentation. And as for the future work, well, basically the next steps are going from simple graphs to hypergraphs and doing some real keenness because it's nonsense. And that's the end of my talk. Thank you very much. Time for questions. To be very quiet.
We try something, so I'm not sure if I followed everything, but so in the case where you have what you call the tree,
yeah.
So assume you take something very simple. So you have these two Poisson rivals with the same intensity,
yeah.
And you have to match them.
Mm-hmm.
So this conservation law would apply to the change, right?
Mm-hmm.
And so
but the system will be unstable as there will be the Q size will evolve at square root of t. So
yeah, I understand that, but but the conservation rule works, right?
Mm.
Because so the output rate of this matching would be the input rate of the Q.
As long as the Q evolves.
My question is really about this notion of stabilisation in terms of the Q size being converging to something or not exploding, but it would make sense to develop a framework where you just want that this Markov chain be recurrent, because it could be in that case. It would oscillate, right? It would have a large but if it so there will be infinitely often times where this Q empties, right? And this conservation, if I get it correctly, these conservation rules of yours would hold, right?
Yeah.
And so my question is whether one can address also this extension to your framework to this case of that the thing be perhaps not stable in the sense that you say is the weakly converging, but something weaker so that they don't explode linearly.
For me, and actually this is what I did there. Yes, you see that I just took a very large Q and okay, it works. And so from my point of view, but you know that I'm not very good with that type of things. Yes, most of things should hold, but maybe Anna has a different opinion on that. I don't know.
It depends on what type of results. Like, for example, the algebra part.
Yeah, it would all. For the algebra part, all you need is the graph to be sublinear. Yeah.
Then for I don't know for others, I'm looking forward. To some extent, the trick of seeing the arrows from pairs is one way of dealing with this issue. Because if we are by default in the reference case, not in the positive reference case, at best, it can be transient from no reference. If we authorize one item at a time, but then by coupling the arrivals, we can study it more precisely. So I think many results can be extended, but with some care.
Yeah, another thought on that. So I know we probably disagree on that, but maybe the practical way to do it is to introduce abandonment. Actually, introduce abandonment. to go back to the positive recurrent case. I know you disagree with that, but you like to study things.
You can also trigger a dependent point processes as input. It's another way to, because you have this non-recurrent because of the independent of Poisson,
yes,
right, which is like the wrong mode. But if you would take 2 point processes which are correlated enough so that they don't lag too much one ahead of the other or behind the other.
Yeah, but in some way you will fall back to the bipartite case, and it's the way the bipartite case is studied. Actually, you couple the higher value on the left and on the right. Yeah. So yes, you could do that as well. But here it will be strange to assume arbitrary things, and for a specific vertex to say, okay, we will change the rules, and the input will be coupled between this vertex-specific left part and this vertex-specific right part.
Yeah, another related question also is how much all these things depend on the Poisson assumption, because you can define these things for more general point processes. And some of these conservation rules are just very natural. They don't rely on it. So the Poisson creates something perhaps interesting with this non-recurrence, but so there might be frameworks where your several inputs will be jointly stationary, and these equations will hold. So the other global question is, what can you say about how to use this machinery for the non-Poisson input?
So here, this is just my guts speaking. For the bijective and surjective only cases, I believe that most of the results will hold, because it's just the long-term behavior that you want to study. With exception of the vertices, because when you go to the vertices, you can have something that is injective only, and so we got back to the issue. So if you don't want to reach one injective only vertex, the arrival type of arrivals should not matter that much. Well, of course, you want to have some finite moments and things like that to avoid, hardcore case. So I wouldn't put my hand to cut for, say, heavy tail distribution or things like that. But for not heavy tail distributions, yes, strongly think you can take pretty much what you want. Maybe it works for heavy tail as well, but like I say, it can be tricky, that type of things. For heavy tail, we could have a hypergraph issue. So it is possible, for instance, that the Nongreedy policies are not stable anymore and that you need something more powerful.
That's one more question, but I don't want to take so you could also have the assumption that the matching takes some time, right? And your queue would be slowed down by the operating matching, right?
Yeah.
You want to make a bike, so it takes time to put the screw. So
okay, so we would like to pipe this with a standard service queue.
Yes, right. So the principle of this equation would work for matching the inputs and the types, right?
Yeah, but for instance, one big issue is that even if the matching IRval is Poisson, the departure rate is not Poisson anymore. You've got lots of dependencies that happen.
Yeah. Sure. Yeah. Right. But so so for instance, in the simple case where you will have no choice,
complete graph, yes,
graph, something like that. Then you have the max plus formalism and all the machinery is there for the text to compute. Right? So that would be. So here the novelty is that you have plenty of choices on this point.
But even for a complete graph, actually, it's not Poisson, because you have two cases. The cases where the thing is empty, and so you kind of stash an arrival, and it's not empty. If you fall on the non-empty heap, you will stash as well. But for instance, if you got a big heap and you arrive, you will have instant match. So depending on the size of the heap, the rate of the output will be different. See what I mean? So you will have some distortion as well, even in the case where you have a complete complete graph. The bridge seems to be quiet. Thank you again.
Thank you.